According to the classical electromagnetic theory, electromagnetic energy is carried by waves. This leads us to the belief that energy flows continuously. The wave nature of light was confirmed by Young's double-slit interference in 1801, and then James Maxwell's electromagnetic wave equation in 1865, which was subsequently verified experimentally by Heinrich Hertz in 1887. Just when physicists thought that the light wave theory or EM wave theory was here to stay, people made observations that could not be explained by the wave theory. We will start with the blackbody radiation. First, let me explain what a blackbody is. We see that this block is red because when we shine white light on it, it absorbs all other colors and reflects red light into our eyes. Our eyes receive red light, that's why it looks red. That block is black because it absorbs all the white light that shines on it. It does not reflect light into our eyes, that's why it looks black. Okay, I should really say that it absorbs almost all the light, because there has to be some light getting reflected into our eyes. That's why we can still see this black block. Now, a perfect blackbody would absorb all light, all electromagnetic radiation that falls on it. So it should be perfectly black. That's why we call such things blackbodies. Oh well, this thing is actually kind of tricky. It turns out that a perfect blackbody does not have to be black at all. Because although a blackbody cannot reflect any EM radiation, it can emit its own radiation. This block looks black because of its low temperature. So it gives off very weak radiation, and its radiation mainly has wavelengths longer than the visible light. So we cannot see its radiation. However, let's look at the heating elements of my waffle maker. When it is cold, the heating elements appear black. Wait and see what happens when it heats up. When it's hot, it looks orange because of the radiation it emits. The radiation emitted by a blackbody held at a constant uniform temperature is called blackbody radiation. Blackbody radiation has a continuous spectrum, meaning its radiation contains all frequencies, which means all wavelengths within a certain range. If I plot the intensity versus wavelength graph, it will look like this. 1. The distribution of intensity for various wavelengths depends on the temperature of the blackbody. 2. The total amount of radiation emitted increases as the temperature increases. 3. The wavelength with peak intensity decreases with increasing temperature. That's why a star's color has to do with its temperature. Our sun is about 6,000 kelvins, with peak intensity at around 500 nanometers. So the sun appears yellowish-orange. A star with higher temperature would have peak intensity at a shorter wavelength, so it may appear to be green or blue. It turns out that classical electromagnetic theory or wave theory of light predicts a spectrum like this for blackbody radiation. It provides a good fit for long wavelength range, but fails completely for short wavelength radiation. Then in 1900, Max Planck announced that by assuming that the energy of electromagnetic radiation emitted or absorbed by a molecule is quantized, he could correctly predict the blackbody radiation spectrum. Max Planck said that the energy of any molecular oscillation could only be a multiple of HF, where the n is the quantum number, it's a whole number, and the f is the frequency of the oscillation. This idea is called the Planck's quantum hypothesis. The h here is called the Planck's constant. and h is 6.63 times 10 to the negative 34th joules second. Joule times second. This is a standard unit one, so if everything you put in your equation is in standard unit, then this is the one you would use. For this one, that is eV times second. This is not the standard unit, but if you use electron volts for energy, then this is the one you want to use. An analogy that contrasts the quantum theory with the classical theory is the stairs versus ramp analogy. On the stairs, a box can only have a certain amount of gravitational potential energy, quantized or discrete amount of gravitational potential energy. On the ramp, the box's potential energy can change continuously. Therefore, according to the quantum hypothesis, in a black body, only those atoms and molecules with energy that is more than hf can give off radiation with frequency f. Atoms and molecules with less energy than hf cannot combine their energy to give off radiation with frequency f. For very high frequency or very short wavelength radiation, it takes atoms and molecules of very high energy to produce such radiation. Therefore, fewer atoms and molecules can emit such short wavelength radiation, hence the decrease in intensity at shorter wavelengths. The success of Planck's quantum hypothesis in explaining the spectrum of blackbody radiation made people doubt the wave theory of light by suggesting that energy is discrete and not continuous. It was a difficult to accept weird new concept. Besides, the wave theory was so good at explaining the interference, diffraction, and the polarization of light. So it wasn't until 1905 when Einstein explained the photoelectric effect using quantum hypothesis that physicists felt more compelled to accept the quantum theory. So stay tuned, and we will be studying photoelectric effect very soon.